Okay. Do you see the red dot on your, is it blinking?
Yeah.
Okay. All right, Josh, thank you so much for coming today. I am going to be asking you some questions.
Okay.
Mostly about sinking and floating today, okay? And I just kind of want to know your thoughts about why some things sink and when some things float. And we have a couple of things that I'm going to put in the water. If you have something that you're having a hard time explaining and it's easier to draw, I have paper and pencils here.
Mm-hmm.
Let's give you a fresh piece of paper. And if, or if there's something that you say that maybe I don't understand, I may have you draw it, and I may have you, if you say some terms, kind of explain what those are as well.
Okay.
Okay? So, I guess you've been in the bathtub, you've been in a swimming pool, and you've seen that some things kind of float at the top,
Mm-hmm.
and some things sink to the bottom. And I'm wondering if you can explain to me why that might happen.
So, if I were to give like a sentence or two,
Mm-hmm.
it'd be on the weight of the water, as opposed to whatever's sinking or floating in it, and there's a little more than weight too. There's density involved.
What do you mean by that? What is density?
How tightly packed something is the best way I can describe it. If the more dense it is, the more tightly packed it is. So if
What is the it?
uh,
So let's
whatever-
take this ping pong ball,
mhm.
okay? How tightly packed the ping pong ball is?
Yeah. How is there a lot of room inside it? I mean, I don't necessarily mean hollow, which that ping pong ball is, though.
Right.
Yeah.
Well, we can take this, the wood block.
Wood block, right? It's more porous. I mean, it has a lot more little holes in it. But it seems, and there could be room where you could take that and sort of just squish it in if that was possible without breaking it. If you can just squish it in, and suddenly, like, you have every single molecule, atom, piece of wood that made it up still in there, but it's suddenly occupying less space than it was before.
If you squish it together. That's what
Yeah.
you're saying. Okay.
So, in that case, it'd be more dense because everything's a little more tightly packed.
Okay, all right, now go back to your explanation. You were talking, there's more involved than weight, there's density and,
It's mainly weight and density. In the case of boats, it could be both those things as well as the shape. Because I haven't really, I don't usually see the bottom of a boat from the outside, but on the few pictures I have seen them, it's sort of a weird shape. It enters in, sort of it's thin down bottom and it curves out, sort of like that. And yeah, that's sort of how I've seen them. So,
okay. So I have a couple things here that we're gonna actually
Mhm.
test out, and I want you to explain what happens,
Okay.
okay? So the first one I held up was a ping pong ball.
Yeah.
Will this sink or float?
float, sorry. Getting my words mixed up.
Okay, and why do you think?
It's made out of light material. Water could get in it, but not as easily if it's just on the surface. It's lighter than that water is. I mean, like if you were able to, like if you were able to hold up this, and if you're able to hold up that water, or even just put this in a cup of the same weight as that, so you could really feel the difference, the water would be heavier. The cup with the water in it would be.
Okay, so you're weighing water, ping pong ball, water. is
Water would
weighing
be
a lot
heavier,
more.
and the water wouldn't be able to get inside the ping pong ball as easily to equal it out more and make this sink.
Okay, let's try it,
Okay.
see what happens.
Drop it in.
Mm-hmm. Okay. Is there any of the ball under the water?
Yeah, a little bit. But
Why do you think that happened?
because
Why isn't it all just sitting on the top?
because it's still, there's still a weight to it. It still has some mass. It's still gonna the water. I mean, the water. Um, so should I describe what surface tension is? If I
Sure.
want to go, all right. So surface tension um, has to do more with the bonds created by the 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 polar molecules in of water, H2O. If I remember right, hydrogen has a positive charge, and oxygen will have a negative charge, and this will create hydrogen bonding
Mm-hmm.
between them, and it really links things together. And
Hydrogen bonding, you're saying hydrogen to hydrogen?
sure, well, it's so if I were to I have my here's my oxygen, and then these different colors for hydrogen. I have my two hydrogen.
Mm-hmm.
So that's my water. And if I have another one, then it's been so long. I have my other H2O right here. If this has if these two have positive charges, and this has a negative charge, positive and negative sort of doesn't you don't say H2 I don't know. So there's
Where are you getting stuff?
in the bonds between them right here. I'm pretty sure I can't remember exactly.
So you're trying to get the positives attracted to the negatives
Mm-hmm.
to kind of hold together?
And it's this whole idea of this polar positive negative,
Okay, so the way that you've drawn this, you have lines coming from the positive
and that's
age to the negative.
yeah,
Oh.
and it's sort of the bond, and I can't really remember too much, or maybe it's I can't remember if it's the hydrogen's bond or the
Okay, well,
Whenever-
you were saying this because it was surface tension, and
It's-
you wanted some argument for surface tension to explain.
So,
So go back to that.
surface tension what'll happen is things that are light enough, the water instead of the water just sort of enveloping it, you can actually see like the water is being pushed down,
Mhm.
and that's the whole water sort of being bonded together, sort of being one. And if it's light enough, then it won't break up the water and it won't sink. And that's why you see these bugs. They have this with the water bugs that have 4 legs. They're already light, and their legs will typically be wide apart.
Mhm.
So you have this weight that's that's distributed even more over a larger space, so it doesn't break up the water
Mhm.
as much, and they can just sort of rest on top of the water instead of sink down below them, and or their legs being enveloped by it. And this is sort of the same thing. The golf the ping pong ball isn't breaking that surface tension. It's sort of resting on top of the water instead of just below it, or even further down, or just sinking altogether.
So does the surface tension help it float?
In the case of the ping pong ball, I don't know if the surface tension is actually part of it. If it was another thing, it could be that was lighter. The ping pong ball could just be lighter.
Like a water bug?
Yeah, you have all this air also in the ping pong ball, and if you've ever blown a bubble underwater, the air goes up, and that's because it's lighter than water. It's in the gas state for one,
Mhm.
and all the things you're breathing out. So, gases being lighter than liquids or solids would float up typically, unless it's a pretty heavy gas, but I don't usually see bubbles that sink down, so I'm pretty sure most gases would sink up.
Think of one right now. Okay, what is this?
That's a little piece of wood.
Okay, and what do you think that is gonna do?
So it could do one of two things. It could sink immediately, but my bet's more on floating at first, and then it's going to sink down.
Okay.
And that's because it's porous. Like I said before, it has all these little holes in it that allow the water to get through, and this wood will become waterlogged, meaning it's filled with water.
Mm-hmm.
And once it's filled with water, it's going to be heavier. If this was larger, to make a better example, you could have a log that might be hollow at first, a little light, that you could pick up, but then you get it waterlogged. You got all this water in it, and suddenly it's a lot heavier. You won't be able to pick it up as much, and that's actually happened to me. My friend and I were at a lake, and there was a log that we were trying to clear all the logs from the area that were in the water, and they were all so much heavier than they would have been if they were dry,
Okay.
because they could hold in all this water, and water can be pretty heavy when it's a lot
And
of
those
it.
logs were already out of the water, right?
They started in the water, and they would have been so
Were
much
they
lighter.
floating or sinking in the water
They were
on the ground?
they were like below the water. They would just sort of peek up a little bit,
Mm-hmm.
and
And why
So
did
you
they
can see
peak
them.
up?
Most likely it would because one end would be smaller. So I mean, it's not going to be so even. It's going to be distributed, which means one part will be larger. The part that has more of it will be able to hold more water and be heavier. So this lighter part will be able to stick up more. So usually,
So the lighter part
which will usually
is
be
at
thinner.
the top, and then the thicker part at the bottom.
Hmm.
Okay. Put that in the water and see what happens. Okay. Is there any bit of that under the water?
Yeah.
Okay. How does that relate to your surface tension? Consistent with what you said before?
I wouldn't actually bring surface tension in much on this one. There could be more
Okay.
than I know there is, but
And why not?
I don't know. It could be. Actually, I'm more. Could I divert it a little bit?
Yeah.
I'm more interested in a little bit how it's resting on the water,
Mm-hmm.
because as I described, boats on the bottom have this sort of, if you want to call them, a diagonal shape.
Mm-hmm.
So it's a little more curved, and this is resting diagonally just like a boat would be.
Mm-hmm.
So that could be more into the shape instead of resting as with its one side sort of parallel to the surface of the water.
Mm-hmm.
It's resting, so it's sort of going in.
Right, so instead of like this,
Mhm.
it seems to be falling with the point.
Yeah, and could I try that with other?
Yeah.
It would be. So it's doing the same thing with all the other
The
sides.
other sides.
Mm-hmm. So that would be more of the shape, and that. So the shape seems to help with.
Okay. Do you think it'll float like this?
No. And that's because it's light. At this point, it's light enough that the majority of it will be above the water. So if you have this small, not very stable part below the water and the majority is above, that's definitely not very stable, and we'll just swish
Mm-hmm.
right down. And, I mean, it almost seems sort of logical just to think that if you just look at it, it would just be like, no, it wouldn't really happen.
Okay. This is an interesting thing.
Mhm.
Okay. Do you know what this is?
No.
It is a popper.
Oh.
You know, you can
Yeah,
drop
yeah.
them and they pop up. But we're going to use it for this. Okay, so I'm going to move the wood block over to our float container. What do you think's going to happen here?
So it depends, I think, a little bit on how we put it in.
Okay, let's say we put it in this way.
I think it could float at first. It might start bubbling up through there, and then it might start sinking faster than the wood would be. Wood doesn't seem to be sinking yet, but
I actually
I
have
think-
two of these, and we should do one like this and one
okay.
like this. Where did I put them? Here they are, right behind you. I like your, what would happen if we did it different ways. Okay, so we're gonna put one in this way and one in this way.
Okay.
What do you think's gonna happen?
So the thing that's throwing me off the most is the hole on
Mhm.
top. If you put it in this way and made sure it was even, I would say float immediately, because you suddenly have, when you put it in this way, the water comes up and then you trap all this air that was inside.
Mhm.
But with this hole, the air is not trapped. So I can't say I'd be as sure, and I'd go more
Okay, let's, if
sink.
it's trapped, okay,
Mhm.
what does the air have to do with making this float?
It's pushing
Why is
up.
that important?
Air wouldn't. So, air in its gas state won't, in, with all the things that's in this room, all the molecules, it wouldn't mix with the water. So you have two things that won't mix, and if this is lighter and less dense, it's going to go on top. And if it's pushing its way against the water and against this, it's sort of going to be keeping itself above the water and then keeping this thing above too.
Mhm.
But now that the air's not trapped, I can't say there's anything stopping it from just.
Right, because we've got a hole in the top.
Mm-hmm.
Okay, why don't you try both? You said it's important to keep it even. Oh,
So it sank there.
so what happened?
Air escaped through the hole.
Okay, and so it was, you've been saying heavy weight?
Mm-hmm. But if this sinks low enough so the water gets over there, then it will definitely start sinking faster than it was at the surface. But if it's able to rest, say like there, and I think it'll sink slower. I mean, water might come up through there because if you think about water and air fighting, I guess the water is stronger. It'd push the air out of this little hole and start maybe filling up, but slower because you have this small little entrance. And then I think this one would sink at first. I mean, not sink, float at first, but then it might start sinking later.
Okay,
And
let's see.
so,
Can you see what's going on?
mm-hmm. Yeah, it's filling up, and then once it hits the rim, it starts sinking. Yeah.
There we go. Okay, so explain that process.
So, it rested close to the rim of the bowl of that little popper. The water did, and then it started pushing its way up through the little hole, and as it, and you could see it actually started even going down a little more as the weight of the water filled up the bowl.
Mm-hmm.
But
You could see it like on the outside.
Mhm.
It was kind of.
that was
down.
sort of, it was lower here, and it was slowly rising, and at the same time, this whole bowl was starting to sink because of the weight of the water that was sort of pushing it on it down, but immediately once it hit the rim, and it just collapsed all at once, and I think that's because of the pressure that the water has. There's more water, more fluid on the outside, and so that's pushing it up more, and there's less on the outside, on the inside, pushing it down. But once it reached an equilibrium from the inside and the outside, then there was nothing pushing. They were both pushing on it with the same force, and it just sank because it was heavier than the water.
Okay, I want you to draw me that in like 3 stages.
Okay.
Like where it was at the top, the middle, and at the bottom. And
Alright.
you were kind of talking about pressure and arrows and
Yeah.
forces. Try to include that in your drawing.
Okay, so here's like a little cross section of that bowl,
Mhm.
and the water, once it stopped, stayed about at that level. But there was a little hole right here, and the water started coming up. So if you use green as our little, use arrows for the pressure, then we have a small arrow from the water here pushing it down,
Mhm.
and because the water's pushing it down, and then you have all this water on the outside, and that's going to create a larger force that's counteracting that. And then at the same time, it's a bowl shape and it's about even. So, just to explain why it's not tipping
Mhm.
or anything, you have this even arrow on opposite sides pushing it from the side. So,
Okay.
yeah. And then, so that's step number 1. It starts coming up. And then step number 2, you have the same bowl. And now the water's a little higher. And so this arrow is going to become bigger. It's going to start having more weight, more push to it.
What is giving it that push?
So
You have something pushing down. What is that?
So it could be, for one, the weight of the water. As I said before, I mean, water's heavy. If you just pick it, if you have like a container full of water, it's going to be a lot heavier than if the container was empty.
Mhm.
And also, I think it'd be, I don't know how much of this is true, but you have these molecules. It's a fluid. It's not quite as solid. They're not going to be as resting as much as they are. They're still going to be bouncing around everywhere. So you have the water molecules hitting against this rim as well as each other,
Mhm.
and so that's also going to be pushing it down.
Okay. And then the pushing up.
Pushing up. So now with the weight of the water, this is fighting back a little more. So this is gonna, so the water is gonna increase a tiny bit, not as much, not to make a significant difference.
The water on the outside you're talking
Mhm.
about. Okay.
And so these are gonna have about the same push. Again, so maybe a little more, but I don't think it'd be
Mhm.
as big as it was before. Or I mean, it wouldn't make as big of a difference as the next step, where now the water has suddenly reached the rim. So you have the rim, and by now, this has been increasing as this water has been increasing, but not as quickly.
Increasing within the container, so it's getting. That's what you mean by increasing.
So
Getting
the
higher?
water around it is getting higher.
Oh, the
and
water
going
on the
toward, Yeah,
outside.
sorry. Yeah, going towards the rim of the bowl, and they'll meet about the same time. If one were to beat the other, it'd be one on the outside. It might tip in a little bit. Some water might tip in, but it looked like it happened pretty quickly, and they almost met at the rim of the bowl. And now you have this water, and the arrows are just as big. So the force on both sides is just as big, and now the water isn't going to be affecting it as much, or well, I mean, it's creating an equilibrium. So it's equal on both sides.
So then why doesn't it just stay kind of like hovering at the top?
Because it still has some weight to it, and it's also, even in the water, it's still going to be affected by gravity a little bit. So, well, not just a little bit, it's going to be affected by gravity. And so this weight will, actually, I'm going to stick more with the weight of it.
Mhm.
It's heavier than water. I felt it felt heavier than that. Not heavier than the whole bowl itself, but from what it was dealing with at the surface, and so it sank down towards the bottom, because this is equal, but this is still heavier than the water would be. I can't explain it very well.
What part are you stuck on?
I can think about it through my head, and I can think about it logically, and it's like you have. I mean, it's just I've never been good at explaining many things, so
You're doing an excellent job.
I just
I think your explanation is great.
Mhm.
I'm trying to figure out where you're getting stuck.
it
You're trying to say something, you're stopping yourself.
yeah it's trying to. So the water is equal on both sides, and
Equal on both sides, the top and the bottom.
it still has weight on both sides. So now the water, you can almost disregard the water because it's putting an equal force on the top and bottom. So it's like if it were in air, though with its weight and gravity that pulls it down, its mass, it would still sink. Like you would drop it, it would just fall.
Mhm.
And I don't want to do it because I've been diving. When you're in the ocean, it's like you're in a weightless environment. So that's why I sort of cut myself short when I said gravity still affects you in the water. But I don't know at one point where to stop myself there.
Do you think you could explain it using the term density instead of forces and weight?
Okay. So you could think about it. Things that are more dense typically like to get on bottom, and you could think about it like you have a bunch of sprinkles, and then you have cereal.
Mhm.
Say Frosted Flakes. Sprinkles, when you have them in a pile, there's not going to be as much air between them as there will be in between the Frosted Flakes. And if you were to put the sprinkles on top of the Frosted Flakes, then they would rest there. Some of the sprinkles might slip through the cracks of the Frosted Flakes. If you were to shake it,
Mhm.
or somehow get something in there to stir it, the sprinkles would start to fall and fall and fall, and they would start getting underneath the Frosted Flakes. And that's the whole concept of the simpler concept of how things with the higher density will get underneath things with a lower density. And yeah.
Okay, so how would you compare the density in this picture to the density in that picture? It's the same object, right?
Mm-hmm. So so the water it's been getting on top here. It's sort of, and it's increasing. So if you look at it and the water's increasing and this is already starting to sink, then you could come to a conclusion that the water is less dense than than the popper is. So when the popper's more dense, it'll sink through.
When the popper's more dense.
Or
How is it
when it doesn't get more dense, but the popper is more dense, and once the water stops forcing it upwards and it's equal on both sides, then that density really comes into play and it sinks through. So it stays the same density. That was bad wording on my part.
Okay, I think that's great. All right, how do you feel about that?
I use too many words, but I mean that's sort of, I've always done that.
I think you did a really nice job. Okay, I'm gonna stop the tape.